In the previous session, we have seen what are determinants, why they are important, and how to evaluate them. Now let's look at some properties of determinants. Determinant of A is equal to the determinant of the transpose of A. So let's take a 3 by 3 matrix. So determinant of A is equal to determinant of this matrix. Now, determinant of A is equal to, we know how to evaluate. So A11 times A22 times A33 minus A23 times A32 minus A12 times A21 times A33 minus A23 times A31 plus A13 times A21 times A32 minus A22 times A31. Okay, opening up the brackets, we get this expression. Now let's take the transpose of A and evaluate the determinant. So transpose of A will be rows become columns and columns becomes rows. So A11, A21, A31. Now again evaluating the determinant of this transpose, you have A11 times A22 times A33 minus A32 times A23 and so on. Again opening up the brackets, we get this. Now since multiplication is commutative, rearranging the factors in the terms, we get A11 times A22 times A33 minus A11 times A23 times A32 minus and so on. Now compare the determinant of A and the determinant of its transpose. So let's compare it term by term. A11 times A22 times A33. So these two are equal. Let's look at the second term. A11 times A23 times A32. They are also equal. Now A12 times A21 times A33 plus A12 times A23 times A31 plus A13 A21 times A3 and similarly the last. So term by term when we compare, they are both equal, which means that the determinant of A is equal to the determinant of the transpose of A. So that was our first property. Let's look at what happens to the determinant if we interchange two rows. So the way we write that is Ri interchanged with Rj. So interchanging two rows so that the ith row becomes the jth row and vice versa changes the sign of the determinant. So let's again take it step by step. Determinant of A is the determinant of this matrix. So evaluating the determinant, we get this expression, and opening up the brackets, we get this. Now, let's do the interchanging, first row and the second row. So when we do that, what happens? After interchanging, the determinant of A becomes determinant of second row becomes first row becomes second row. So we have A21, A22, A23, A11, A12, A13, A31, A32, A33. Now let's evaluate the determinant of this. So again, following the logic, we evaluate. Opening up the brackets, we get this. Now again, we rearrange the terms. We get this. Minus A22 times A11 times A33. And here if you see A11 times A22 times A33. So here it is plus, here it is minus. And similarly, if term by term we compare, then they are of opposite signs each term. Which means if you multiply this by -1 throughout, they will become equal. Determinant of A is the original determinant. After interchanging a row, the determinant becomes minus the determinant of A. Okay, now let's look at the next property. Interchanging two columns. So interchanging the column positions so that the ith column becomes the jth column and vice versa changes the sign of the determinant. Now, how do we prove this? Interchanging two columns of a matrix is equivalent to interchanging the corresponding rows of its transpose. Yes, because when we take the transpose, the rows become columns and columns becomes rows. So if we are interchanging two columns of a matrix, it is equivalent to interchanging the corresponding rows of its transpose. So column swap in A implies row swap in the transpose of A. And row swap in the previous property, we have seen that it implies sign change in the determinant. So determinant of A, the new one, after interchanging is equal to the determinant of the transpose of A after row swap, which is equal to minus the determinant of A transpose, which is equal to minus the determinant of A. That was interchanging two columns, changing the sign of the determinant. Now, two common rows or columns. That means two rows have the same values and two columns have the same values. So, either one of these. So, if two rows or two columns of a determinant are identical, then the determinant is 0. So, let's take a 3 by 3 matrix and let's look at its determinant. So, evaluating it, we get this. And here you notice that this particular matrix of which we have taken the determinant, two rows are identical. A11, A12, A13, A11, A12, A13. So when we evaluate it, you will notice that three terms and three terms cancel out to be left with 0. So if two columns of a determinant are identical, then its transpose has two identical rows. And just now we have proved that two identical rows means the determinant is 0. So hence the determinant of the transpose of A is equal to 0. Since determinant of A is equal to determinant of A transpose, it follows that determinant of A is equal to 0 after interchanging the columns. Common factor in a row or column. If the elements of any row or column are multiplied by the same scalar k, then the new determinant is k times the original determinant, which means we can simplify the determinant by factoring out common factor of a row or column. So let's see 3 by 3 matrix A. Let's say B is equal to A11, A12, A13. That means the first row of A and B are same. Similarly, third row of each are also same. But the second row in B is a k multiple of the second row of A. So now, normally following the process, we evaluate the determinant of B. And here you will notice that every term has k as a common factor. So let's take that out. So we have A11 times k times A22 times A33 minus A23 times A32 minus A12 times k times A21 times A33 minus A23 times A31 plus A13 times k times A21 times A32 minus A22 times A33. A31. Now, these three terms have K in common. So we take it out. So we have K times the rest of the terms. Expression which is inside the square bracket is nothing but determinant of A. So we can say determinant of B is equal to K times the determinant of A. What this means is that if we are given a matrix in which a row has some common factor, we can factor it out while evaluating the determinant. Now let's look at linearity of the determinant in a row or column. If the elements of any row or column are sums of two quantities, then the determinant can be expressed as the sum of two determinants of the same order. So, suppose this is the given matrix where one of the rows is a sum of two quantities. We have A11 plus P, A12 plus Q, A13 plus R. Let's evaluate the determinant. Open up the bracket. We have, after opening the bracket, if we group them, now how have I grouped it? I have taken PQR separately. A11, A12, A13 separate. Determinant of A is the sum of these two. Now, what is the first bracketed expression? That is nothing but the determinant of A11, A12, A13, A21, A22, A23, A31, A32, A33. Whereas the second bracketed term is the determinant of PQR A21, A22, A23, A31, A32, A33. So, if in a row we have a sum of quantities, then we can evaluate the determinant by taking the determinants separately and adding them. Hence, the determinant is linear in each row or column. Okay, now next property, zero row or zero column property. If a row or a column consists entirely of zeros, then the value of the determinant is zero. So something like this, we have a matrix with a row as zeros. Along the first row, if we evaluate the determinant, we get this. Now the bracketed terms will all become zero, and that multiplied with anything will be zero. So the determinant of A is zero. Now along the second row, if we take, then the values which are outside these bracketed terms will be zero, which means the entire thing will be zero. And along the third row, again, if we evaluate it, the bracketed terms will all be zero. So overall determinant of A is zero. Thus, irrespective of the row chosen for expansion, each term contains a zero factor, hence the determinant is zero. So that was zero row or zero column property. Let's look at the determinant of a triangular matrix. If a matrix is triangular, that is upper or lower, then its determinant is the product of the elements of its principal diagonal. So let's see. So this is upper triangular matrix. Determinant will be, if we evaluate it, we get A11 times A22 times A3. Rest all will become zero. So which means for upper triangular matrix, the determinant is the product of the elements of in its principal diagonal, A11 times A22 times A33. Now let's look at lower triangular matrix. So same process. Here again we end up with A11 times A22 times A33. So that was properties of determinants. That's it for now. Bye.